Software-defined networking is a new term that's only been around since about 2009, and it's been described as the hope and/or hype of the future of networking. So the hope is really to address some problems with networking in the modern internet age, things like how we scale the management of networks, which is currently very complex, how we give applications easier access to the networking so they can communicate with different computers and other smartphones and other tablets and things like that. And also the important issue of virtualization, which is where we take resources in data centers and virtualize them across several users who can all share the same resources, which is more efficient. So the challenge facing software-defined networking is traditionally networking equipment is very monolithic, single-function boxes, a bit like mainframe computers were back in the 60s and 70s when you bought your hardware, your operating system, and all your software from the same people. It's a bit like that with networking equipment to this day, where you buy the hardware, you have the manufacturer's software running on it, and a few applications which are provided by the provider of the equipment. So the challenge for us is to take this monolithic picture and try to disassemble it a bit while still running at the very fast networking rates we need in the modern internet. So basically what's going on is we're trying to split the equipment in three ways. There's a bottom layer which is called the data plane, which is where the actual data is being transmitted over the network at very high speeds. And then above that we have the control plane, which is the thing that manages the operation of the data plane, a bit like the operating system, if you like, managing the resources. And then finally, we have the applications level, where applications can use this underlying operating system in the control plane and then use the networking resources. So that's the mission, is to split these into pieces. And what we need are well-defined APIs, that's application program interfaces between the layers. The so-called northbound API sits between the applications and the control plane. And the one that's of most interest to us is the southbound API, which sits between the control plane and the data plane. And that's because the data plane is where Xilinx FPGAs naturally fit. Xilinx FPGAs are very important for high-speed networking and very programmable smart networking in particular. If we have a look at this southbound API, one of the first defined schemes for doing it is called OpenFlow, which originated at Stanford University. And the starting point there was a very simple view of the data plane, where it has limited functions and limited programmability of the functions. And then the OpenFlow API allows software to control that interface by setting up tables. Now what we can do with FPGAs is put a lot more smartness into the data plane, so we can have more programmability, more responsiveness to the control plane. So if we have a look at that southbound API, if we have something more intelligent in the data plane, then in one direction, coming from the software down to the data plane, we have programmability, that's how the software tells the data plane to behave. And that can range from simple things like configuration control registers, through to things like setting microcode in the data plane. And for Xilinx FPGAs, we can have a partial reconfiguration that actually changes part of the hardware in the data plane, or even full reconfiguration, which allows you to change the functions completely inside the FPGA. So that gives a lot richer programmability and hence potential smartness in the data plane by having a wider range of functions in there. In the other direction, the data plane has to report back to the control plane to explain what's going on. And at its simplest, that could just be keeping counters of packets and the amount of data that's traveling through the data plane and giving that to software. But then we can do more elaborate things like computing statistics at networking speeds before we send it back to the software, or doing more elaborate things such as computing so-called sketches, which are probabilistic analysis of the data that give better feedback to the software about what's really going on. And at the end of the day, that means the data plane can do a lot of the work and pre-process data about what's going on before the software has to take control. So the effect of having this richer programmability in one direction and richer analytics in the other direction means that the FPGA is providing a lot more smartness in the data plane, something that's not possible with a simple ASIC, which is just there to do simple routing and switching of packets. So one benefit of that is at the moment, software-defined networking is very often confined just to data centers where there's slower speeds on one hand, and there's less programmability on the other hand, just simple switching. What we can do with the smarter networking enabled by the Xilinx FPGA is to take this out into the carrier networks, the high-speed networks, and bring this software-defined networking into the wider world outside the data center. So at the end of the day, what we really have is a partnership between the software, which, as in software-defined networking, and the programmable hardware, which is where Xilinx specializes. So overall, I like to call it softly-defined networking. We have a lot of softness. It's not just software code, but also softness in the hardware. So the all-programmable FPGA.